Hello Year 13 and welcome to your first flip lesson of the year. We're going to be studying the hydrolysis of esters and we're going to be looking at a few biological molecules that are relevant to what we've been studying. These are the specification points we're covering. I've skipped a couple out because they are referring to just stating things, like stating that esters are used for perfumes and stating the use of fatty acids as biofuels. We'll talk about that in the lesson a little bit, but I'm not going to waste my time or your time here talking about them. Okay. So, we're going to be talking about ester hydrolysis. We know by now pretty well how esters are made from esterification. So hydrolysis means splitting using water. Lysis means splitting hydro water. It's really slow unless you use an acid or a base as a catalyst. So, if you want to hydrolyze our ester in hot acid, this is the equation. I've used R and R prime. This is R prime. This little, the apostrophe here is referred to as a primed. We had water and acid in the form of aqueous acid. You wouldn't normally see it written as H2O plus H plus. You normally see it as H plus AQ. We're making our carboxylic acid and our alcohol. So we're getting back to our starting materials. In conditions of reflux, we need a hot acid, and we want the acid to be aqueous. The water is the reactant, but the acid is a catalyst. Okay, so the water is going to react. You can see that it's added in here. We've added H2O across these two molecules. And the H plus is actually regenerated. I've not put it on both sides of the equation, but it is. Okay, so what about in hot base? Well, it is largely the same. We've got on the left hand side our ester, R and R prime, water, and my base of choice is sodium hydroxide. And on the right hand side we've made our carboxylic acid and we've made our alcohol and we've regenerated sodium hydroxide. But sodium hydroxide plus carboxylic acid, that's going to be an acid-base reaction. So we can react further to make the carboxylate salt, the alcohol, and the water. The examiners are very anal about this, so please make sure you pick up on it if they're asking you for hydrolysis with base, and do not leave your acid with a proton attached to it. So this is the general equation if we weren't to put this middle step in. You notice the name, that sometimes it's called saponification. I'm going to talk a little bit later about why we call it saponification. Okay, so what about fatty acids? Fatty acids are the first biological molecule that we're going to be talking about. And they actually get quite a lot of press, particularly with a nation heading towards obesity. They're basically just carboxylic acids with a very long carbon chain. I believe the most simple fatty acid is butanoic acid, but generally we're talking at least 8 or 10 carbons, up to any number you like really. They're important within the body. Some of them are useful, some of them are detrimental. They come in three types: cis-unsaturated fatty acids, trans-unsaturated fatty acids, and saturated fatty acids. Saturated fatty acids and trans fatty acids you may have heard talked about in health programs. So saturated fatty acids. Saturated fatty acids here, you can see that it's got hydrogens on all of the carbons. It is saturated with hydrogens. Here is an unsaturated fatty acid. It has double bonds, therefore there is not a hydrogen on every carbon. It's not full of hydrogens. It's not saturated with hydrogens. So saturated fatty acids, no double bonds in their carbon chains, and they've been recognised as being bad for you for quite a long time. What about unsaturated fatty acids? Well, there are two varieties of these. They've got a double bond in their carbon chain, fairly obviously. There's two varieties. We can either have trans or cis fatty acids. The trans fatty acids are the ones that are bad for you. Cis ones are quite good for you. But why the difference? Well, really it all comes down to melting points. Clearly the same, they have the same rough structure, they have the same chemistry. However, the cis fatty acids have a very different spatial arrangement. And that means that they can't stack together very well. The cis fatty acids, you see, are bent. They can't stack with each other, okay? whereas the trans fatty acids are straight. They can stack with each other, and the same as saturated fatty acids, they're also straight. They can stack on top of each other. So if they can stack on top of each other, you can get a lot of contact between the two chains. Okay, you can get a lot of contact. You can have a lot of van der Waals forces. They're going to be sticking together very well. If you don't have very much contact, like in this case where we're bending off to the right or to the left, we can't get very much contact, you're not going to have very high van der Waals forces. You're not going to have a very high melting point. So trans and saturated fats tend to be solid and form globules, and cis fatty acids tend to be oily. So if we have something that is going to stay as a solid, it's very hard for the blood to dissolve it, for it to be moved off the inside of our blood vessels and our arteries, and thus it builds up, and we end up with cholesterol deposits and other deposits of fat around our arteries and around our organs. This is bad, obviously. This is fat around the inside of our arteries and blood vessels, cholesterol on the inside of our arteries and blood vessels, can cause heart attacks because it will cause blood clots. If it gets in the way of the blood going to the brain, that can give us a stroke. So generally, it's very bad news. So how we need to know, it said in our specification thing, how to name fatty acids. Now I'm first going to teach you the longhand way. You could be asked either way. We take our carboxyl carbon, that's the carbon with the carboxylic acid on it, as 1. We only need to put the number of carbons then, the positions of any double bonds. So, for example, here we have a fatty acid. It's a cis fatty acid, you'll notice. What I find quite interesting is it's drawn very straight here, but actually it would be incredibly bent, so there wouldn't be any contact. We'll count our carbons. We have 18 carbons. So this is where we need to know our Greek numbering. So 18 is octadeca. We have a cis bond, which is a Z. The cis bond is in the 9th position, so we have Z octadeca 9-enoic acid. Okay, remember that an enoic acid at the end. If it was fully saturated, we wouldn't have to worry about the number. It would just be octadecanoic acid. Simple. There is an easier way there, the shorthand way. One I think is easier. It's kind of a numerical way of numbering it. And it comes off the idea that the only things that are going to be different between fatty acids are the number of carbons, the number of double bonds, and their positions. So we use what's called the delta notation. And I've quite complicatedly represented it here as X, Y, brackets Z. Okay? Where X is our number of carbons, Y, the number of double bonds, and Z, the position of the double bond. So for the same fatty acids, remember we have 18 carbons, 1 double bond, and it's in the 9th position. It would look like this: 18, 1, brackets 9. Trouble with this is it doesn't tell us whether the bond is cis or trans. Final bit of biology for us, hopefully for the rest of this course, is about glycerol and triglycerides. Glycerol is kind of like a sugar. It's in jelly. It's very, very gloopy because of the large amount of hydrogen bonding between these OHs. So trial. The systematic name is propan 1,2,3 trial. Being a trial, it has the potential to form 3 ester bonds. If we mix it with some fatty acids, we can esterificate it 3 times, up to 3 times. If we esterificate it once, that's a monoglyceride. Twice, that's a diglyceride. 3 times, it's a triglyceride. Triglycerides you've probably heard of. Final thing we're going to talk about are triglycerides. They look like this. We have 3 fatty acids and some glycerol. Here are carboxyl groups. And you'll notice that we've kind of lost our polarity here. So, the most naturally occurring fats and oils are where triglycerides are found. Our saturated triglycerides are going to be solids at room temperature because they're going to stack very nicely. Our cis unsaturated ones are going to not stack very well. Our trans fatty acids are going to stack very nicely. When we hydrolyze our triglycerides, that's called saponification as well. That is the original hydrolysis, if you will, and that's because the fatty acid products we use to make soap, fatty acids, as you can probably work out, are very good for soaps, and in fact I'm going to leave you with that to work out as a little bit of thinking before the lesson. So that's it for this week. This is hopefully going to be 2 lessons worth of video, so I expect you to come prepared with your notes on Friday. Look forward to seeing you then.